Hi everyone, today a video looking at redox reactions. So the word redox is short for reduction oxidation, and there are a few different ways we can define reduction and oxidation. The first is kind of a simplistic picture of it. An oxidation reaction is one in which we have an addition of hydrogen, and likewise a reduction would be a loss of oxygen. Another way to think about it is that typically if we have gained oxygen, we would have lost hydrogen. So we can think of an oxidation reaction as a loss of hydrogen or a reduction reaction as a gain of hydrogen. And so, for example, these couple of equations here, we have copper reacting with oxygen to make copper oxide. We would say that the copper has been oxidized because it has gained oxygen. Then the second reaction here, copper oxide plus hydrogen, it produces copper and water. And we'd say here that the copper has been reduced because we have essentially added hydrogen to the reaction, and the copper oxide has lost the oxygen to reform copper. But really the way that we should be thinking about oxidation and reduction is in terms of electrons. And we say that oxidation is a loss of electrons, reduction is the gain of electrons. So, as we said, when something's oxidized, it loses electrons. When something is reduced, it gains electrons. And the easy way to remember this is to remember the phrase oil rig. So oxidation is loss of electrons, reduction is gain of electrons. And so really when we think about whether something's been oxidized or reduced, we can think about it in terms of whether it's gained oxygen, lost oxygen, gained hydrogen or lost hydrogen. But really, if we're asked to define oxidation or reduction, and really when we look at reactions, we need to be looking at whether it gains or loses electrons. So going back to our examples using copper here, we said that copper plus oxygen to make copper oxide was an oxidation of copper. And sort of very simply, it's gained oxygen, so it's an oxidation reaction. But if we start to think about it in terms of electrons, what we need to start doing is starting to consider the ions that we make. So copper is our atom, it just exists as copper. Our oxygen is a covalent molecule, but then our copper oxide is an ionic species. We have our copper 2 plus ion and our oxide 2 minus ion. And so clearly what has happened here is 2 electrons have been lost from the copper. We've gone from neutral copper to copper 2 plus. We must have lost 2 electrons. And our oxygen has gone from being neutral to a 2 minus anion. So we've had electron flow essentially from the copper to the oxygen. And so when we're talking about the copper here, well, the copper has lost electrons and therefore it has been oxidized. For the other reaction, the copper oxide plus hydrogen to make copper and water, we said that because the copper oxide had lost oxygen, that this was a reduction reaction in a very simplistic picture. But we can look at it from electron flow. Again, copper oxide we can think of as being a copper 2 plus cation and an oxide 2 minus anion. Hydrogen is our covalent molecule, so H2. And then on the other side, we can consider our copper to just be copper, neutral copper. But our water we can think of as being an oxide 2 minus anion and 2 lots of H plus cations. And so what's happened here is our copper has gone from being 2 plus to neutral. In order for that to have happened, we must have gained 2 electrons. And so when we've gained electrons, that is reduction. Now we can also look at the hydrogen. The hydrogen has gone from being a neutral, H2, to becoming H+. So how this could have happened is going from neutral hydrogen to H+, it must have lost an electron. Remember that the losing of an electron is oxidation. And this is why we call these reactions redox reactions or reduction-oxidation reactions. Because reduction and oxidation have to happen together. We can't just have one thing being oxidized or reduced. If something is oxidized, something else must be reduced. Something gains electrons, something loses electrons. We have to have the electron flow from one to the other. And so in this second example, we can see essentially we have electron flow from our hydrogen to the copper. 2 plus cation, which gives us copper and protons. Now also notice we have the O2 minus anion, the oxide anion, appearing in both sides of that equation. And you can see that it doesn't change, and so that's something that we call the spectator ion. It's in the equation, but it doesn't actually really get involved in the reaction. And if we go back to our first equation, we said that the copper was oxidized because it lost electrons. Well, we can actually say that our oxygen has been reduced because we started off with neutral oxygen, O2. We've then gone to O2 minus. So the oxygen has gained 2 electrons and therefore it must have been reduced. So the really takeaway key thing here is to think about things in terms of electrons, and also that oxidation and reduction have to happen together. If something's oxidized, something else must be reduced. So the equations that we've been looking at on the previous slide are the full stoichiometric equation. For example, copper plus a half oxygen to copper oxide, or copper oxide plus hydrogen to copper and water. These are the full balanced equations. But we can start to consider something else called half equations, and these are really important when we have redox reactions. Essentially, we can split our full equation into 2 equations, 2 half equations, that when we combine these half equations, we get our full equation. And so essentially, we're going to take the partner that is oxidized, write an equation for that, and the partner that is reduced, and write an equation for that. So in the first example, we had copper plus a half oxygen to copper oxide, and we said that the copper had been oxidized because it had lost 2 electrons to become copper 2 plus, and that our oxygen had been reduced because it gained 2 electrons to become O2 minus. And so we can write 2 half equations for this. The copper becomes copper 2 plus, and then like a normal balanced equation, we have to make sure that all the atoms balance. We also have to make sure that our charges balance. And so copper going to copper 2 plus, we have a 2 plus charge on the right hand side, we have neutral on the left hand side. So we have to add 2 electrons to our right hand side in order to conserve the charge. And so that's showing us that our copper becomes copper 2 plus and loses 2 electrons, i.e. it's oxidized. For the oxygen, we have a half O2 going to O2 minus. Note that we've balanced that, not just O2 to O2 minus, but a half O2 to O2 minus. And then because we have a 2 negative charge on the right-hand side, we need to add 2 electrons to our left-hand side. And this is showing us that our oxygen is gaining 2 electrons and being reduced. We can also do the same thing for the second reaction, the copper oxide plus hydrogen reaction. We know we start with copper 2 plus in the copper oxide, and that ends up producing just elemental copper. And so we have a 2 plus charge on the left hand side, neutral on the right hand side, so we have to add 2 electrons to our left hand side, and it shows us that our copper 2 plus ion gains 2 electrons, i.e. it is reduced. Likewise, we then consider the hydrogen, so we have H2 going to 2H plus. We've got a 2 positive charge on the right hand side, neutral on the left hand side, so we need to add 2 electrons on our right hand side to balance the charge, and it's therefore shown that our hydrogen has lost 2 electrons, i.e. it's been oxidized. So the really key thing is that if we write our half equations, we have to consider both the oxidized partner and the reduced partner, and we have to make sure that our atoms and our charges always balance. So time to have a go at a few questions. Essentially, it's working out what has been oxidized and reduced and writing some half equations. So if you're going to have a go, pause the video and the answers will be on the next slide. So the first question was copper oxide reacting with magnesium. This produces magnesium oxide and copper. And so we're asked to write, essentially split this into its ions and find out which has been oxidized and which has been reduced. Now, whenever I do any redox question, I always have to write oil rig down somewhere on the page, just at the side of the page, at the top of the page, just so I can always remember that oxidation is loss of electrons and reduction is gain. So the copper oxide will be copper 2 plus and O2 minus. Our magnesium is just elemental magnesium, so we don't change that. The magnesium oxide will be a magnesium 2 plus ion, and then our oxide O2 minus anion, and then our copper is elemental copper. So when we look at this, we can see that our copper 2 plus has ended up becoming elemental copper. So the copper must have gained 2 electrons, and if we've gained electrons, the copper has been reduced. And then our magnesium has gone from being elemental magnesium, neutral magnesium, to a magnesium 2 plus cation. And so the magnesium must have lost 2 electrons, And so we say that because we've lost electrons, our magnesium has been oxidized. And then note again in this example, we have our O2- anions present on both the left and the right hand side. So our oxide ions are just spectator ions. They're present in the equation, but they don't actually get involved in the reduction of the oxidation. So then writing out the half equations, well, we just use this information we've just kind of got from the equation. So we have copper 2 plus, it goes to copper. And then to balance the charge, we have to have 2 electrons on the left-hand side. So copper 2 plus 2 electrons goes to copper. And likewise for the magnesium, we've started off with just elemental magnesium. It's become magnesium 2 plus. And so to balance the charge, we have to add 2 electrons to our right-hand side. So magnesium goes to Mg2 plus and 2 electrons. Again, if we write half equations, like we do for full equations, make sure the charge is balanced and make sure the atom number balances. Then, second question, we were told that solid aluminium reacts with copper oxide. And so if we think about the reaction going on here, which I've drawn out at the bottom in the green, we have aluminium reacting with copper oxide. And we're going to get a simple sort of ion displacement reaction, the swapping around of the ions. So we end up with aluminium oxide and copper. So clearly our aluminium has gone from being neutral aluminium, elemental aluminium, to an aluminium 3 plus ion, and therefore it has lost 3 electrons. If this is the case, then we say the aluminium has been oxidized. For our copper, we must have gained 2 electrons because we've started with copper oxide, copper 2 plus. We've ended up with elemental copper, and so the copper has gained 2 electrons to become the neutral copper, and so the copper has been reduced. So the aluminium has lost the electrons, oxidized, copper gained the electrons, reduced. Now something we didn't cover was how to combine half equations to make the full equation. And the way that we do this is that, notice in the full equations, when we talked about the copper oxide reactions with the hydrogen and stuff, that there's never any electrons in a full equation. So to get from our half equations to our full equation, we must cancel out the electrons. And this is why it's important to have our half equations written down. We have aluminium going to Al3 plus 3 electrons. We have copper going to copper 2 plus 2 electrons to copper. And so the only way we can get these electrons to cancel out is if we times the aluminium equation by 2 and the copper equation by 3. This would give us 6 electrons on both sides, and therefore they would cancel out just to leave us with the overall equation. So we end up therefore with 2 aluminium going to 2 Al3 plus 6 electrons, and 3 copper 2 plus going plus 6 electrons going to 3 lots of copper. So then we just write down everything that we have on our reactant side, everything we have on the product side from both equations on the product side. So we have 2 aluminium plus 3 lots of the copper ions plus 6 electrons going to 2 of the aluminium ions, 6 electrons and 3 coppers. And then our 6 electrons on both sides are the same, so they cancel out. It's like having plus 2 and minus 2 almost. And so we then end up with 2 aluminium plus 3 lots of copper 2 plus going to 2 lots of aluminium 3 plus and 3 lots of copper. And so if we wanted to write out our genuine full equation, because of course in this case the oxygen again would be the spectator ion, we'd have 2 lots of aluminium plus 3 lots of copper oxide to make aluminium oxide Al2O3 plus copper, and 3 lots of copper. So then we come on to look at something called redox agents. So the first thing to remember here is our oil rig expression. Oxidation is loss of electrons, reduction is gain. But as well as talking about, for example, a certain element being oxidized or reduced, we can talk about reducing agents and oxidizing agents. So reducing agents are some things that reduce something else. So a reducing agent will reduce another component of the reaction. And so if the reducing agents reduce something else, they themselves must be oxidized. So our reducing agents donate electrons, and therefore they are oxidized. They lose electrons. Oxidizing agents oxidize one of the partners in our reaction. And so if the oxidizing agents oxidize something, they must be reduced themselves. Remember that oxidation and reduction have to happen together. And so oxidizing agents accept electrons, and they themselves are then reduced because they've gained electrons. And the easiest way that I kind of remember this is that it's the opposite of what you think. So a reducing agent, reduction is normally gain, but a reducing agent loses electrons and therefore is oxidized. Oxidation is loss, so an oxidizing agent is the opposite, it gains electrons and is reduced. So if we go back to our copper plus oxygen reaction to make copper oxide, we can see that our copper goes to copper 2 plus, so we can write our half equation, copper going to copper 2 plus 2 electrons. And so we know that our copper has been therefore oxidized, it has lost electrons. And so if it has lost the electrons, it's been oxidized, it must be the reducing agent. Likewise for our oxygen, in this case we have a half O2 going to O2 minus, so therefore the half O2 must have gained 2 electrons. If it's gained 2 electrons, then we say the oxygen has been reduced, and if it's been reduced, it must be the oxidizing agent. And we can also do the same thing for the copper oxide plus hydrogen reaction. We have copper 2 plus in the copper oxide going to elemental neutral copper. So our half equation is copper 2 plus 2 electrons to copper. So the copper here has gained electrons, that's reduction, and therefore the copper is the oxidizing agent. Our hydrogen has gone from being H2 to 2H plus and 2 electrons. So therefore our hydrogen has lost electrons, it has been oxidized, and therefore it is the reducing agent. So it's kind of always the opposite of what it actually is. If it's been reduced, it's the oxidizing agent. If it's been oxidized, it's the reducing agent. So this then brings us on to oxidation states. And so each element in a compound will be given an oxidation state. And essentially it's a very theoretical thing to write down, but it kind of represents the number of electrons that a certain element can gain or lose. And so there are a few general rules for this, that every element in its uncombined state has an oxidation state of 0. So what I mean by that essentially is when we have an element just on its own, for example copper on its own, if we have aluminium on its own, that will always have an oxidation state of 0. If our oxidation state is a positive number, it shows that electrons have been lost. Remember that loss of electrons from oil rig is an oxidation. A negative number for our oxidation state shows us that electrons have been gained. Remember that the gain of electrons is reduction. And so essentially you can think of it as like if we've lost electrons, we'd be left with a positive ion. So that's a positive oxidation state. If we'd gained electrons from a neutral state, then we would then have a negative charge, and therefore we have a negative number for our oxidation state. So essentially we're looking at going from our uncombined state, our elemental state, have we lost or gained electrons? And so the kind of very specific rules for oxidation states are as follows. Hydrogen is normally +1. For example, when we looked at the water earlier on, H2O, oxygen we saw is the O2 minus anion, so we say that our oxidation state of oxygen is -2. And therefore, because it's H2O, to make it an overall neutral molecule, we have to have our hydrogen being +1. Another example would be in HCl. Our Cl has an oxidation state of -1. Think of it as a Cl minus anion and an H plus cation. And so normally hydrogen is +1. The only exception to this is if it's in a metal hydride. Now the reason for this oxidation state kind of rules is that we can sort of base it off electronegativity. If something is more electronegative, it's going to have the negative oxidation state. It's more likely to have gained electrons. It's more happy to have electrons and hold on to them. So for example, HCl, chlorine is more electronegative than hydrogen, and so our chlorine takes the oxidation state of -1, while our hydrogen takes the oxidation state of +1. The exception is if it's in a metal hydride, for example, sodium hydride, and this is because our metal, our sodium, is actually electropositive, more electropositive than hydrogen. So the hydrogen actually is the more electronegative atom in this case. And so our hydrogen takes the -1 oxidation state, and our sodium takes the +1. And that kind of looks familiar. We think of that as a sodium plus, Na plus cation. That's a 1+ charge, so it has a 1+ oxidation state. And so generally we can extend that further. Group 1, for example, sodium, potassium, rubidium, they'll always be +1. So the example is sodium chloride. The sodium is a plus ion, the chlorine a 1- ion, and so we have a sodium oxidation state of +1, a chlorine oxidation state of -1. So make sure we always give the sign of our oxidation state. Group 2 will always be +2, so magnesium, calcium, always be +2 because these form +2 ions. So calcium chloride, the calcium will be a +2 ion, and therefore it's an oxidation state of +2. And therefore our chlorines, to make it overall, because we have a neutral molecule overall, we have to have a neutral oxidation state overall. Our chlorines will be -1 oxidation state, because they're a -1 ion. Aluminium is in group 3, and therefore it's a +3 oxidation state, so aluminium trichloride. Aluminium is a 3+ ion, so a 3+ oxidation state. Our chlorines -1 ions, and therefore each chlorine has a -1 oxidation state. Now, the other distinction here, we have 3 chlorines, so overall those 3 chlorines give us a -3 oxidation state to balance the +3 of the aluminium. But because we have 3 chlorines, we have to kind of split the overall oxidation state into 3. So each chlorine has an oxidation state of -1. Now, oxygen is normally -2. We've seen this previously. If we take water again, for example, our hydrogen is normally +1. The oxygen is the more electronegative element, more likely to have the negative oxidation state. And so to balance the 2 +1 oxidation states of the hydrogen, we have to have a -2 oxidation state. Another example would be sodium oxide, Na2O. Here, our sodium we know is a +1 ion, so a +1 oxidation state. We have 2 of them, and so to balance this, to make it an overall neutral compound, to balance the oxidation states, our oxygen must be a 2- ion, and therefore a 2- oxidation state. Now, the only exception to this rule is if we're in something called a peroxide. This is where we have an oxygen-oxygen single bond, or where it's in compounds with fluorine. Now, if it's in a peroxide, for example, hydrogen peroxide, H2O2, our hydrogens are +1. We have 2 of them, so overall we have a +2. We have 2 oxygens, and therefore to make it neutral overall, we'd have to have these being -1 each. We couldn't have them being the normal -2, because that would give us an overall oxidation state for the whole compound as -2. And if we have a neutral molecule, we must have overall the kind of sum of the oxidation states must be neutral as well. The other exception is if it's with fluorine, and that's because fluorine is the more electronegative element. And so if we have the compound F2O, the fluorine is the more electronegative compound. It's going to have a more electronegative element, and so it's going to have the negative oxidation state. And so our fluorine will be -1. Think of it as an F- anion, -1. We have 2 of those, so to overall make it neutral, we have to have a +2 oxygen. Now, fluorine, being the most electronegative element of the periodic table, is always -1. There's no exceptions to that, so an example being sodium fluoride, NaF. The fluorine must be -1, and therefore to make it neutral overall, the sodium must be +1. And then finally, chlorine, normally -1. It's again a fairly electronegative element. So example, sodium chloride again, sodium being +1, to overall make it neutral, the chlorine must be -1. The exception for this is if we have, if it's in a compound with a fluorine or an oxygen, and the reason for that is because the fluorine and the oxygen is more electronegative, and so that will contain the negative number, and so therefore our chlorine must be a positive number. And so generally, our sort of general rules, if we have uncombined elements, like we said, just kind of elemental aluminium, elemental copper, stuff like that, elemental sodium, that will have a 0 oxidation state. It's also true if we have polyatomic elements. So this is elements where they've bonded to themselves, so Cl2, H2, Br2. It also extends to things like dioxygen, O2, dinitrogen, N2, as well as some slightly larger ones such as phosphorus, P4, sulfur, S8. If we have this system where it's just bonded to itself, that's also an oxidation state of 0. And as we said, the sum of all the oxidation states in a neutral compound must equal 0. If we have an overall electrically neutral compound, our oxidation states must add up to 0. If we have an ion, then the sum of the oxidation states of that complex ion must equal the charge on that ion. So if our ion has an overall +1 charge, the sum of the oxidation states must come to +1. If our ion has an overall charge of 2-, our oxidation state sum must come to -2. And generally, in a compound, the most electronegative element has the most negative oxidation state. So, some examples here to have a go at So to work out the oxidation state for all of the elements in the following compounds. So pause the video and the answers will be on the next slide. So a couple of general rules as we said before. If we have a neutral compound, the sum of the oxidation states must be 0. If we have a complex ion, then the total of the sum of the oxidation states must equal the overall charge of that ion. And the way that I always go about this essentially is to look for the most electronegative element first, because we know that this will be the most negative number. And so the first example is phosphorus pentachloride, PCl5. The most electronegative element there is chlorine. And so remember we said that chlorine is generally -1, Cl minus 1 minus anion. So generally chlorine is -1. And therefore, because we have an overall neutral molecule, we have 5 chlorines, so 5 times -1. So we have -5. To make it overall neutral, we have to have our phosphorus being +5. For ammonia, NH3, we said that generally our hydrogens were +1. We can look for our most electronegative element, which is the nitrogen, so that will have the negative oxidation state. So the hydrogen in this case is the more electropositive. It has the +1 oxidation state. Again, ammonia is neutral, so if we have 3 lots of +1, to make it neutral overall, our nitrogen must be -3. For nitric acid, HNO3, the most electronegative element here is the oxygen, and so therefore this will have the most negative number. And we know that oxygen generally, unless it's in a peroxide or with fluorine, is -2. And so the oxygen we can say is -2. We have 3 of these, so 3 times -2 is -6. Now the next easiest thing is to look at the hydrogen. Hydrogen we said, unless it's in a metal hydride, is always +1. And here we have hydrogen with nitrogen and oxygen, very electronegative elements, so the hydrogen is +1. And so we have our -6 from our oxygens, our +1 from our hydrogen. Overall, we need to get to a neutral 0, and so our nitrogen must be +5. The copper oxide, copper oxide, CuO, is look for the most electronegative element, our oxygen, that will be -2, and therefore to make it overall neutral, we have to have a +2 from our copper. E is again another copper oxide, but now we have Cu2O. Our oxygen again is the most electronegative element, -2, but this time to make it overall neutral, again the sum of our copper stuff has to be +2, but because we have 2 coppers, we have to split that +2 oxidation state by 2. And so each copper is actually a +1 oxidation state. So you can see here that some elements can have multiple oxidation states. You see copper having +2 and +1, nitrogen having -3 and +5. And so sometimes they kind of relate to the ions that we'd see in the CuO copper oxide. The copper would be a +2 ion, the oxidation state is +2. In the Cu2O, the other copper oxide in E, our copper would be a +1 ion, it has a +1 oxidation state. But sometimes the oxidation states really don't match up with what kind of the ions would look like. So for part C, we've got nitrogen with a +5 oxidation state. Now clearly this isn't a nitrogen in a +5 nitrogen ion. F, the sulfate anion, SO4 2-. Here we have a complex ion, so we have to make sure that our oxidation states overall add up to -2. We look for the most electronegative atom, which is the oxygen. That will be -2. We have 4 of them, so overall we're going to have -8 for our oxygens. And therefore, to get an overall -2, we have to have -8 plus 6 to get overall -2. And so our sulfur is +6. Part G is the ammonium ion, NH4+, again another complex ion. We have to make sure the sum of this adds to 1 plus 1. We look for our most electronegative element, that's the nitrogen. So therefore the hydrogen is more electropositive. It will have the positive oxidation state of +1. There's 4 of them, so that's +4 overall. And so to get +1 overall, when we have +4 from the hydrogen, means that our nitrogen must be -3. The phosphate anion, PO4 3-. Again, look for the most electronegative element, is the oxygen. There's 4 of them, so that -2 of the oxygen times 4 becomes -8. It's a complex ion with a 3- charge, so we have to overall have the sum of our oxidation states equal -3. And so in order to do that, we have to have a +5 on the phosphorus. And then finally, sodium nitrate. Look for the most electronegative element. Again, it's the oxygen, and so our oxygen is -2. We have 3 of them, so that will give a -6 overall. Then the easiest one to look at is the sodium. So the sodium, we said, being in group 1 is always +1. And so we have -6 from the oxygens, +1 from the sodium. We have a neutral compound overall. And so we then have to get a neutral. The sum of our oxidation states has to be 0. And we achieve that by having nitrogen equal +5. So generally, look at the charge on your ion or look to see if it's overall neutral. Find the electronegative element, the most electronegative element, and then make sure that everything adds up either to the charge or to neutral. So this then brings us on to balancing redox reactions. And as we said earlier on, charge and atoms must balance, like in a normal stoichiometric equation. And so first of all, if we're balancing redox reactions, first of all is we balance the atoms as we would normally for any normal equation. The first thing we'd always do is balance our atoms. Now, typically these kind of questions will say that you have, for example, copper going to copper oxide, and you need to write the half equation and then balance the overall equation. So the first thing is to balance the atoms in the half equation, like we would for any normal equation. Then we're going to, if we've got any excess oxygens, we need to add water molecules to balance those oxygens. By adding water in, we introduce oxygen atoms to balance any oxygen atoms that we have already. Then, by introducing water, we've added hydrogen in, and so to balance the hydrogens, we add in hydrogen ions, protons, H+. And then finally, we've had to add in hydrogen ions, we've now introduced charge, and so we add electrons to balance the overall charge, to make sure the charge on both sides, the left-hand side and the right-hand side, matches up. And then, as we saw earlier on with combining half equations, if we want to combine our half equations into a full equation, we have to make sure that our electrons cancel out. So we may have to multiply some equations by certain numbers to make sure that we have the same number of electrons on the reactants side as we do the product side. Now, when we combine half equations, we always cancel out our electrons, but sometimes you might also be able to cancel out other species, such as water or hydrogen ions. Basically, look at the equation, see if there's anything that exists on both the left-hand side and the right-hand side, and if it does, you can cancel it out. And so this is easily seen if we do some examples. So let's say that our example here, a question might be, for example, that we're told that copper goes to copper 2+, and the nitrate anion, NO3-, goes to NO2, nitrogen dioxide. And the question would be something along the lines of find the half equations and to balance the overall redox equation. And so take one of these at a time. So I'm going to start with the copper equation. So we know that copper goes to copper 2+. And so the first thing I'm going to write down is just simply copper going to copper 2+. And now we have to start going down our checklist that we saw on the previous slide. The first thing is to balance the atoms. Well, that's already done. One copper on the left, one copper on the right. Then we said we had to add waters if there was any oxygen atoms. Well, there's no oxygen atoms, so I don't have to add water. Because I've not added any water, there's no hydrogen atoms, so I don't have to add any protons. But I do have to make sure the charge balances on each side. And so to get over on the left-hand side, we have neutral copper. The right-hand side, copper 2+. So to balance the charge, I have to add 2 electrons to the right-hand side. Now for the nitrate equation, so we have NO3- going to NO2. That's the first thing I write down. Then I look to see, first of all, really, is my nitrogen balanced? And it is. I've got one nitrogen on the left-hand side, one on the right-hand side. I then look at the oxygens, and I see that I've got 3 oxygens on the left-hand side, but only 2 on the right-hand side. And so this is where, when we go down our checklist, we have to add in a water molecule. We add in 1 H2O. In adding in 1 H2O to the right-hand side, we now have 3 oxygen atoms on both sides. However, we've now also introduced hydrogen atoms, because H2O, and so we have 2 hydrogens on the right-hand side, and so we have to add 2 protons, 2 H+ ions, on the left-hand side. And then finally, by adding in these protons, we've added some positive charge in. So overall, on the right-hand side, we have a neutral right-hand side, so no charge. We have a negative charge from our NO3 and 2 positive charges from our protons on the left-hand side. And so overall, to make that neutral as well, we just have to add in 1 electron to make it neutral on the left-hand side. Then the final step was to make sure that our electrons can cancel out, so make sure we have the same number of electrons. And you can see that essentially we've got 2 electrons in the copper equation, but only 1 in the nitrate equation. So we need to times everything in that nitrate equation by 2. And then once we've done that, we write everything from each equation that's a reactant on the reactant side, everything that's a product on the product side. And this gives us copper plus 2 NO3 plus 4 lots of hydrogen ions plus 2 electrons, going to copper 2+ plus 2 electrons plus 2 NO2 plus 2 H2O. And then we can cancel out our electrons. We have 2 electrons on both sides, so we cancel those out. We look at anything else, nothing else is on both the reactant and product side. So our balanced redox equation for this would be copper plus 2NO3 minus plus 4H plus going to copper 2 plus 2NO2 and 2H2O. So time to have a go at some questions of this. So we have to balance the half equations and also combine the half equations to give us the full balanced redox equation. So the first one, we were told that we have iron 2 plus going to iron 3 plus. This is one of these very simple half equations to balance. We don't have to worry about adding in waters because there's no oxygen. We don't have to worry about adding in hydrogen ions because there's no hydrogen atoms. And so all we simply need to do is balance the charge. And so we have Fe2 plus going to Fe3 plus an electron to balance the charge. And we don't have to worry about balancing our atoms because we have 1 atom of iron and 1 atom on both sides. And so that's already balanced. The manganate one, though, is a bit more tricky. So we have our permanganate ion, MnO4 minus, and we're told that it goes to the manganese ion, Mn2 plus. The first thing to note is that we have 1 manganese on both sides. That's good, we don't have to balance that. But we do have 4 oxygens on the left-hand side and none on the right, so we have to add 4 molecules of water. In adding 4 molecules of water, we've introduced now 8 hydrogens, and so we have to add in 8 H pluses, 8 protons, onto the left-hand side. And then finally, make sure the charge balances, so we have 2 plus overall on the right-hand side. We have our negative charge from our permanganate, 8 positive charges from our protons, and so essentially you can think of overall we have a 7 plus charge, and so to get 2 plus on both sides we have to add 5 electrons. Then we want to make sure that our electrons balance so that we can cancel them out, and so we look to see we have 5 electrons in our manganese equation, 1 electron in our iron equation, and so we need to multiply the iron equation by 5 to get 5 electrons. Once we've done that, we can then combine the 2 half equations. Everything that's a reactant becomes a reactant, everything that's a product is a product. So we have MnO4 minus plus 8H plus 5 electrons plus 5 Fe2 plus going to Mn2 plus 4H2O plus 5 Fe3 plus 5 electrons. And then because we have 5 electrons on both sides of that equation, they cancel out. Have a look for anything else. There's nothing on both sides again, so it's just the electrons that we cancel out. And overall, our balanced redox equation becomes MnO4 minus plus 8H plus 5 Fe2 plus goes to Mn2 plus 4H2O plus 5 Fe3 plus. And in purple there I've just included what the oxidation state of everything is. You can check these for yourself and have some extra examples of working them out if you'd like. Second question, we had copper becoming copper 2 plus. Again, this is a very simple one to balance. We don't have to worry about oxygens or hydrogens. We just have to balance the charge. Our atoms are already balanced, 1 copper on each side. So to balance the charge, just add 2 electrons to the right-hand side. Then our nitrate equation, a bit more difficult. This time we have NO3 minus going to nitrogen monoxide, NO. So first of all, check that nitrogens balance. They do. However, though, we have 3 oxygens on the left-hand side and 1 on the right-hand side. So we have to add 2 molecules of water to get 2 more oxygens to make it 3 each. Then we've added 4 hydrogens, so we have to add 4H plus to the left-hand side. And then we want to balance our charge, so overall on the right-hand side it's neutral. We have a negative charge from our nitrate, 4 positive charges from our protons, and so to get it overall we need 3, overall neutral, we need 3 electrons. Then we need our electrons to match, we need them to balance to be able to cancel them out. And so the simplest way to do this, if we have 2 electrons in one and 3 electrons in the other, is to times the 2 electron equation by 3 and the 3 electron equation by 2. And this will give us 6 electrons in each of those equations. And so doing that gives us 3 lots of copper plus 2NO3 minus plus 8H plus 6 electrons goes to 3 lots of copper 2 plus 6 electrons plus 2NO plus 4H2O. Then 6 electrons are on both sides, so we cancel those out, and our balanced redox equation becomes 3 lots of copper plus 2 lots of NO3 minus plus 8H plus goes to 3 lots of copper 2 plus 2NO and 4H2O. And again, in purple, I've just put some of the oxidation states of these elements in. Some key ones to note from both equations. Remember that we said that anything on its own in an uncombined state is 0. So you can see the copper on the left-hand side, 0. If we're working out, for example, what the oxidation state of the manganese is in the permanganate anion, it's a complex ion, so we need to have an overall -1 sum of our oxidation states. Oxygen is the most electronegative element, therefore it's -2. We have 4 of them, and so that's -8. And so to get an overall -1, we have to have our manganese being +7. So thank you for watching this video. You can find many more like this on my YouTube channel. If you found it helpful, please consider leaving a review on a tuition website. I offer online tuition for chemistry, so please check those websites out if you're interested in that. And if you need any more help with your chemistry, you can feel free to drop me an email. I'll be happy to help.